In this video, we're going to look at a method of calculating indefinite integrals, or antiderivatives, called substitution. It's based on reversing the chain rule from differential calculus. So remember what the chain rule says. If you have a composition of functions, then you can compute the derivative by taking the derivative of the outside function, plugging in the inside function, and then multiplying all that by the derivative of the inside function. And that's what this equation says. Now, we can look at this equation from a different point of view. Instead of it telling us how to take the derivative of the left side, we can think of this as telling us how to take an antiderivative of the right side. So if we start with the right side, and we want to find an antiderivative, f of g of x will work. But then remember, for a general antiderivative for an indefinite integral, we want to include a plus c at the end, because this general antiderivative actually represents an entire family of solutions, infinitely many functions that could all be antiderivatives. Okay, so here's the formula we had on the previous screen, this chain rule from the opposite point of view, from the antiderivative point of view. Let's see how we could use this formula to help us calculate an integral. Let's suppose we're starting with the integral of cosine of x squared times 2x, integrated with respect to x. Well, we can view this function, this integrand, as if it were written in the form f prime of g of x times g prime of x. We just have to identify the right functions to use for f and g. Well, we want the outside function in the composition to be f prime. So that matches up with the cosine function. We want the inside function in the composition to be x squared. That matches up with g. And then we want the other function in this product, the 2x, to line up with the g prime. So this is what we should be using for f and g. And since f prime is cosine, we can use sine as its antiderivative. And then if we look at the formula, how do we take the antiderivative when we've written things as f prime of g of x times g prime of x? Well, we just need f as the outside function of g. So that's sine of x squared. And then, of course, we want our plus c. All right, this is how you could formally reverse the chain rule. But it's a little bit awkward. If you want to try to write the function you're integrating in this form, you kind of have to know what your f and g are going to be in advance, and you might feel you need to know what the antiderivative of the outside function in your composition is going to be, and that's not always easy. It can be rather cumbersome to use the formula the way it was written on the previous screens. So we're going to use a shorthand instead, and that shorthand involves the notation of differentials. The differentials are as follows. If you have a function y of a variable x, then the differential dy is equal to the derivative of y times the differential dx. So this is a relationship between the rate at which the function y changes as the variable x changes. What does this mean, this notation? Well, remember the idea of a linear approximation. If you pick 2 points on a curve that are close to each other, and you want to know what the slope of the line is that connects them, well, that's approximately going to be the same as the slope of a tangent line at one of those points, if the 2 points are close enough together. Now, if you rearrange this formula to isolate the change in y on one side, you get change in y is approximately the derivative times delta x. Now, the notation with dy and dx instead of delta y and delta x can be thought of as a shorthand for this. And it's a shorthand that expresses the idea that this approximation should get better and better as delta x gets smaller and smaller. By the way, this f prime you see here is the same as the function y prime in this description. Let's look at a picture that illustrates this relationship a little bit better. Here's a function y of x. Let's pick 2 points on that curve and connect them with a straight line. So this secant line goes through 2 points. One of them is labeled with the x value x. And we might want to know the slope of that line. Well, the slope is just delta y over delta x. If we draw a tangent line at the point with the given x value, that tangent line has a slope that should be pretty close to the slope of this secant line. And in fact, the approximation should get better and better if you bring the second point closer and closer to the first one. So that's where we get the expression slope delta y over delta x is approximately the same as f prime of x, the slope of that tangent line. And then again, we're going to rewrite it in this shorthand notation that expresses that the approximation gets better as you, in some sense, take a limit. Let's compute a couple differentials real quick. Suppose your function is y equals x cubed, and you want to find dy. Well, we'd be using the formula dy equals y prime of x dx. So dy is equal to y prime, which would be 3x squared, times dx. That's it. That's all you have to do to calculate a differential. Let's look at another example. Let's say u is 8 times v, and we want to find the differential du. Well, since we've got u and v instead of y and x, we're going to use the same formula, but with this different notation, u and v, and we end up with du equals the derivative of u, which is 8, times the differential dv. All right, that's how you calculate differentials. There's another way of thinking about this that will help you remember how to compute differentials. dy dx is another way of writing y prime of x. So what you can imagine you're doing is starting with this equation, dy dx equals y prime of x, and pretending that dy over dx is a fraction, and then you can multiply both sides by dx. So you don't really want to think of dy over dx as a fraction. It's the derivative. But if we pretend it's a fraction, it helps us to remember this formula that represents this relationship between dx and dy. Let's see now how this is used to calculate an indefinite integral. Let's go back to the same example we started with in this video. So instead of using a function g to represent the inside function, we're just going to denote that with another variable. Let's use a u. So u is the inside function x squared. And then we don't need to use g prime to represent the derivative. We're going to use du dx to represent the derivative. And the derivative of x squared is 2x. So that means the integrand we started with could be written as cosine of u times du dx, integrated with respect to x. So instead of an x squared, I have this u, and instead of a 2x, I have du dx. But du dx times dx, that's what we mean by the differential du. Now that the integral is all in terms of the variable u, we can find the antiderivative. The antiderivative of cosine of u du would just be sine of u plus c. But because our original function was written in terms of x, we want our antiderivative also to be written in terms of x. So we replace the u with x squared, and we're done. This is the same answer we got before using the more complicated looking formula. But we don't have to think of this as memorizing a formula if instead we think of it as just a process where we substitute a new variable to replace an inside function, and the differential calculation tells us how to change the old dx into a new du, or whatever the variables are that we're using. So let's summarize. Differentials provide us a shorthand. It makes it easier for us to apply this technique than if we tried to use the cumbersome notation of f, f prime, g, and g prime. It also turns out that this notation makes it easier to simplify the integral just a little bit at a time, so that you don't have to be thinking all the way ahead to what your antiderivative of your outside function is going to be. This process is called integration by substitution, because if you think about what we're doing, we're using a new variable to replace an expression involving the original variable. Like in the last example, we used a u instead of x squared.